Okay, good morning to everybody. So let's start the morning section. And the first talk will be given by Stefano Iubini of the Institute of Complex Systems, National Research Council. And the title is, as you can read, Negative Temperature Fourier Transport in One-Dimensional Systems. Okay, thank you. 25 minutes.
Thank you very much. This microphone. So I try to, okay, see a bit, okay. So let me thank the organizers for this opportunity. And as you see from the title, I'm going to talk about something more related to statistical mechanics, and in particular about negative absolute temperature states and their role in steady transport setups. So before starting, let me say that this work has been done in collaboration with Marco Baldovin, who is now in Paris, and it is based on this paper we wrote together. And let us start. So the topic is the existence of non-equilibrium steady states in a class of simple one-dimensional models that can attain negative absolute temperatures. What I will show you is that a phenomenological description in terms of a Fourier law provides a consistent descriptions even for these strange non-equilibrium states. So the outlook of the talk is pretty simple. So we start from a review of negative temperature states in equilibrium. Then I will move to out of equilibrium setups. And I will start from probably the simplest example that one can study, which corresponds to a paramagnetic spin chain, and then I will move to less simple examples, okay? So, negative absolute temperature states are rather recent in the history of thermodynamics. The first one who introduced them was Larsson-Sager in this paper in 1949, as he realized that a configuration involving a turbulent hydrodynamic flow with vortices could correspond to an effective absolute negative temperature. Some years later, Norman Ramsey wrote this very complete paper about the statistical mechanics of negative temperature states, basically focusing on spin systems. So you can understand the physical meaning of a negative temperature by looking at the definition of microcanonical temperature. So here you see that if your entropy is a decreasing function of energy, you have a negative temperature. Usually this is pretty uncommon in physical systems, as we are used to a monotonic increasing function, entropy function, but there exist some systems where the entropy is non-monotonic. And it is quite interesting to notice that probably the most known model in physics, which is the Ising model, actually provides, displays negative temperatures. So you can indeed consider a one-dimensional system, a ferromagnetic system. You start on the ground state where your spins are then you can imagine to increase the energy, and then you will end up in a state of maximum entropy where all your spins are uncorrelated. This is the infinite temperature state. Whoa. Oh, okay. But you can even increase further the energy, and thus entering the negative temperature region, sorry, which in this case corresponds to an antiferromagnetic order. So basically, negative temperature states correspond to inversion of populations. And as Ramsey noticed, a relevant ingredient is the existence of an upper bound for your energy. So you need not only a ground state, but an upper bound. Okay, so it is important to say that all this stuff does not correspond to sort of theoretical divertissement, but actually negative temperature states have been experimentally observed. Here are some examples. So this is the first experiment by Purcell and Pound based on the Ramsey's ideas on nuclear speed system. Basically, they were performing nuclear magnetic resonance experiments, and they were able to invert the population of these spin systems and observe the relaxation of the system to again positive temperature states. Here on the right is a more recent example made with cold atoms loaded in optical lattices. So actually this experiment corresponds to a two-dimensional optical lattice. And here the authors were able to show the difference between the equilibrium momentum distribution at positive temperature and at negative temperature. So, and the last very, very recent experiments has been done in optics with the multimode optical fibers. And so basically here, this setup is such that you can observe a thermalization of light. And this plot shows the behavior of the radial intensity of light as a function of the distance with respect to the center of the fiber. You see there is this strange oscillatory behavior, and here it's shown that this behavior actually is very well described in terms of Rayleigh-Jeans theory of optical modes at negative temperature. Okay, so let us come to the point. What we have discussed till now is basically equilibrium, equilibrium thermodynamics. So from this point of view, negative temperature states are quite well understood. There is no, there are no problems. But actually, if you consider out of equilibrium conditions, this is a less studied problem. So what I have in mind is this setup. So consider, again, a one-dimensional system for simplicity, where you have a chain of interacting entities. They can be interacting oscillators, spins, whatever you want, which is in contact at its boundary with thermal reservoirs. So the question is, so what happens if this system is driven to negative temperature? Does it explode? Does it can it sustain negative temperatures? Okay, so of course, if you want to analyze this problem, you have to first of all provide a consistent definition of reservoirs at negative temperatures. Actually, from a statistical mechanical point of view, this problem is can be solved. So let us consider a simple example. So this is a standard version of the Langevin equation for a degree of freedom. So you have some mechanical forces plus, if you want to thermalize it, you put usually a dissipation term plus some fluctuations, which are usually Gaussian, whatever you want. So actually there is a simple recipe to produce negative, to impose negative temperature, just reverse the sign of temperature and reverse also the sign of the dissipation, so that it becomes a gain. So you can prove this from microscopic models, so it works. It is also simple, so we are happy. And so you may ask, so if I impose a gain of energy, does the system explode? The answer is no, because remember that this system have an upper bound of energy, so there is no explosion. Okay, so we have all the theoretical tools to explore this problem, and let us consider the problem in which you have diffusion in your system. We would like to check if a phenomenological law like the Fourier law is still valid. So if you look at the standard form where K is the conductivity and T is temperature, you see that if you go close to the infinite temperature point, this equation is rather strange because you have to cope with infinities. So actually, what I will show is that actually an equivalent version of the Fourier law in terms of a variable beta, so the inverse temperature, is able to consistently describe this fusion even at negative temperature. So you would say this is just a change of variable from the mathematical point of view. So it's trivial, but okay, the physical meaning of this equation is straightforward, I would say. Okay, let us consider this simple example, the paramagnetic spin chain. So we have this Hamiltonian on a line. We have spins +1 and -1. And of course, equilibrium thermodynamics is very, very simple. You can describe the system in terms of the number of spin up. You can introduce this occupation probability P. And then you can compute the entropy density. It's just a matter of simple combinatoric calculation, no? And you get this expression. And as we expected, this entropy function as a function of the density is non-monotonic. This is exactly the problem analyzed by Ramsey in his first paper. Okay, so equilibrium is very simple, it's not so surprising, but let us go to non-equilibrium. First of all, we have to introduce a microscopic evolution. So here, I just consider the simplest example, so a stochastic exclusion process involving nearest neighbor sites, so a spin exchange dynamics, so that you have a local detail balance, so a reversible dynamics, and the conservation of total energy. So in this case, you can write the expression of the heat current in terms of this occupation probability and the transition rates. And you can also find an analytical expression of this current if you neglect non-equilibrium correlations. So if I do this approximation, I can solve, let's say, the problem and write the explicit expression of a non-equilibrium occupation probability, this profile of Pn. As you see, it's a linear profile. It's not so surprising, which is written in terms of boundary probabilities, which are imposed by the boundary reservoirs. So again, boundary reservoirs are known, so you can introduce this beta at the boundary of the chain. And here is a comparison between this theoretical expectation and simulation. So here I'm plotting the non-equilibrium profiles of inverse temperature as a function of the site. You see there is a very good agreement. And you see there is this, you can easily produce these strange profiles that are connecting temperature with opposite signs, and of course, which have to cross the infinite temperature point. Since we have chosen this beta parameter, you have not divergences. Right? And in this model, you can also compute explicitly the form of the conductivity, what I've called gamma, and to plot it as a function of the inverse temperature beta. So you see there is a perfect symmetry with respect to the infinite temperature point, and the maximal conductivity here is attained for infinite temperature. Okay, so this is a first example. Let us go to a completely different one-dimensional system, which is now deterministic. So this model has been widely studied by this group in Rome, by Angelo Vulpiani, and here is the Hamiltonian. You see, you have a nearest neighbor coupling, plus you have a strange kinetic energy. which is now again bounded. In the low energy limit, this kinetic energy, this kinetic operator becomes the standard kinetic energy. So you get a very well-studied model of coupled rotors. But if you take this form, so this is a model which can display negative temperature. So we build up our machinery. We again impose Langevin boundary reservoirs. This is an equivalent form. And again, you see, you get a qualitatively similar scenario for the beta profiles as a function of the lattice position, which are almost linear. So in this case, it's much more difficult to extract analytical calculation, because here the model is much more complicated. Bear in mind that here diffusion is directly produced by the model. The model is chaotic, so diffusion arises spontaneously. Okay, the last model I would like to discuss is this one. So till now we have analyzed some examples where you have just one transported quantity, which is heat, energy. There are more complex situations where you can transport more than one quantity. Let us talk about thermoelectricity, where you can transport heat and current, or heat and mass. So here we were interested to check if this negative temperature scenario was also valid for this class of system. So here we have considered this simple chain of complex oscillator, which is actually corresponds to a Schrödinger equation on a lattice. And okay, so if you look at this model, basically you have a problem, because this model is integrable. So you don't have diffusion at all. You just have a collection of traveling waves. If you want to introduce a sort of interaction between modes, a very effective way is to introduce a conservative noise. This idea was discussed for the first time by these people. So actually, the idea is to add some collision events on phases of these models that it introduce an interaction. So you end up with a model which displays just two conserved quantities: the total energy and the total norm of the wave function. These are the physical quantities that we are interested in. Again, since the model is very simple, you can compute equilibrium thermodynamics very easily. So here, since you have two conserved quantity, the equilibrium properties are described in a two-dimensional diagram, where you plot the density of norm and the density of energy. So one point in this diagram is an equilibrium point. You have the ground state, which is beta minus infinite. You have the infinite temperature line, and then you have the upper energy state. And here, this orange region is negative temperature region. Since you have two conserved quantities, your thermodynamics is expressed in terms of two thermodynamical parameters: the temperature and a chemical potential. And again, we can play the same game. You just add boundary reservoirs. Here is the form of the Langevin equation for this system. And you can impose imbalances. So here is an example of some profiles, from non-equilibrium profiles that you can obtain, just reported parametrically in this diagram. If you look at them in more detail, you see the same qualitative scenario. Here is the profile of beta, of the inverse temperature as a function of space. And here again, you can cross easily the infinite temperature point connecting two temperatures with opposite sign. And the other things that you find is that the conjugated, so the other thermodynamical variable is beta mu, which does not display divergences and so on. So here is a check for diffusion. Here reporting the stationary currents as a function of the system size. And you see you have a 1/n scaling. Even in this regime where I impose temperatures at the boundaries with opposite sign. And let us come to the conclusion. So this is a first preliminary study of thermal transport in one-dimensional models involving negative temperature states. We have considered three classes of systems, basically: stochastic spin systems, deterministic rotor chains, and sort of mixed deterministic and stochastic complex oscillators, where you can transport heat and norm at the same time. So we have seen that this strange stationary non-equilibrium regime connecting temperature with opposite signs are accessible, are physically accessible. There exists a formulation of the Fourier law which consistently describes them, and we have found that the natural parameters to describe these states are beta and beta. So, okay, of course, one would like to better explore this model, better compute these conductivities, and let me conclude with this consideration. In this setup that we have analyzed, basically, you observe negative temperature states as soon as you are able to impose at the boundary at least a negative temperature. So this could seem a sort of limitation. You need a negative temperature reservoir. Actually, so this is not completely true, because there exist examples where negative temperatures are spontaneously produced out of equilibrium. And this is one of these examples that corresponds to a discrete nonlinear Schrödinger equation. So I just consider the last example of the Schrödinger chain. Do not put stochastic noise and add the nonlinearity. You end up with a model which is non-integrable, which is chaotic, so it has very good statistical properties. And here is a non-equilibrium profile, where here you see at the boundaries I'm imposing positive temperatures, and negative temperatures are produced by the system itself in the bulk. So this tells us that in some sense there is this negative temperature scenario is a bit wide. Okay, so these are some papers that where we studied this problem. Okay, so I stop here. Thank you for your attention.
Thank you, Stefano. Right, Alessandro.
Stefano, sorry, maybe I arrived too late, but sorry, maybe I arrived too late. My question is, how is defined a temperature in a way that is negative? Which is the definition of temperature?
So if you consider a microcanonical system, just the derivative of your entropy with respect to energy. Okay. In canonical, you can just consider, yeah, it's a parameter, you can play with it, you can put a negative temperature inside your Boltzmann weight. Of course, you have to play with a system that sustains negative temperatures. So you need an upper bound for your energy. Otherwise, if you put this negative temperature, you explode. Okay.
Franco.
No, it is really interesting. I remember of having read, I think, a footnote about negative temperature in Landau-Lifshitz, first edition, something like this. In the Landau-Lifshitz, for sure, the third edition, there is a whole chapter about negative temperatures. But so, okay, just because you remember that, we can check. Now, I was thinking, how can this have a negative temperature in the middle of positive temperature? Because in principle, when you put in contact, the negative temperatures are higher than positive temperature.
Yeah.
So you should have, say, diffusion of temperatures.
The key point is that you have a coupled transport. So you are transporting not only heat but also noise. And here you have to play not only with the Fourier law, but in a more general way with the Onsager matrix. So in this case, this is the setup where you have to analyze this.
Okay, so it's due to the fact that you have a coupling between temperature and density in some sense.
Yes.
Okay.
If you consider a model with just one conserved quantity, this is forbidden because of second principle, if you want.
Exactly. Okay, thank you.
Any other comment, question? Okay, if not, let's thank Stefano again.
Sì, ho voglia.
No, vabbè, comunque 5 minuti. Okay, we can pass to the second speaker, Michele Baia from the Department of Physics here in Florence, synchronization, control, and data assimilation of the Lorentz system.
Yeah, no? Okay. Good morning, I'm Michele Baia, and next time I'm talking about synchronization, control, and simulation in the case of the Lorentz system. In this presentation, in this work, we try to connect some aspect of the data simulation with and watch the data simulation in a dynamical system point of view, connecting with the master-slave synchronization defined by Pecker and Carroll, and use this result to find to estimate parameter in two different ways when the state variable are directly measurable, or when we know we measure a function, a scalar function of that. So first of all, we introduction in the field, thinking about this, for example, methodological forecasting. We know that the system, or at least the model that describe the system, are chaotic. So in general, it's important to do a good forecasting. We need a good model that describe correctly what's happening in the reality, a series of high quality, high spaced in time and space data source, and a method to connect the data that we obtain by measurement and what the model tell us. So a method to synchronize these two things. To do that, we recall the Pecker-Carroll synchronization, or master-slave, and where Pecker and Carroll in this work define a way to connect, to synchronize two models in a master and a slave, that where a slave is feed putting some information from one system, for example, putting one variable in the other, and they show that for the real system like chaotic circuits or simulated system like the Lorentz system, we can define some direction associate with the associated with a definition of conditional Laplace exponent, that is the Laplace exponent of the subsystem of the slave that can, and they show that the synchronization is done if the condition of the Laplace are both negative. So if the subspace are not chaotic, essentially. We can generalize this definition of synchronization, putting a scheme like that. So suppose we have a master defined by the first equation. We can define a replica area slave system that is coupled with a coupling parameter P, coupling strength, in one direction defined. Because we are interested in essentially in synchronization system with measurement, we can think directly in a discrete mode. For example, using the Euler scheme, we can essentially we can define our system as this map, do a coupling step between the master and the slave, and then evolve also the slave system. To check if the two systems are synchronized, we can define a distance like a simply two norm in the state space. The first work is to analyze if exists a critical value of the coupling strength such that for value bigger than this value, the synchronization hold. We check with the Lorentz system defined by this equation, which is considering this parameter, and we can see that for different coupling direction with this label, we indicate the element of the diagonal matrix of the projector. So, for example, in this situation, we coupling along the x direction. We can find a threshold such that the synchronization hold. Also, we can generalize the definition of the coupling of the sublapone exponent, and we find that where the threshold, the critical value exists, also the Suliapunov become negative. For example, for the zeta direction, the Suliapunov stay almost positive or near zero, and the distance showed in orange in this label, in this plot, say negative, say positive. So synchronization cannot be done along this direction. So, but in general, we have supposed that we can coupling the two systems every time step t. But in general, the measurements are not able every time. So the master is accessible only with a time step different and bigger than our time integration. We check that it's possible to have synchronization also in this case. So essentially, in this case, we evolve our system or two systems freely, and we coupling only when a measurement such as available, and we see that the critical value exists, and if for small time step growing linearly with the time step. So after that, we check, we study what happened when we consider also that the master and the slave system have different parameters. So we can define another distance, the uppercase, that is the distance between the two parameters, and we study the distance. Here we can see a heat map of the distance in the real space when for different parameter value and different distance in the parameter space. We can see that where the synchronization is possible, we can see that the distance smoothly drop to 0. So we can see we can use the distance, the real space, as an indicator of the distance in parameter space, and then optimize the distance in the real space to find the right parameter. So minimize the distance in the real space to optimize the true parameter. We can do for example, with a simulated linking scheme. So starting with a master copy with the right parameter and a replica with random parameter choice by physical plausible value. We establish a coupling direction and a time interval such that exists the threshold P critical, and we apply a standard simulated link approach. So given our value, we propose a change in parameter states of the slave. We evolve the system and we do the synchronization step, we evaluate the distance after t time step. We accept or refute the change if our move are essentially are energy combinant in this sense, or we accept with probability exponential with an exponential decay with the temperature theta. We also obviously decrease the temperature theta to essentially accept only energy convenient move. In this sense, in the simulated annealing, this distance is a sort of energy. Is a sort of energy. We can see that when the temperature drops to 0, for different coupling direction, we can obviously obtain the right parameter. Also, so the distance between the parameter of the master and the slave drop to 0, and we can optimize the value of our system. But in this case, we are supposed to know all the system, or in particular, we suppose that we can have hash to hold the system because we measure the distance d as the difference of the distance in the real space. But in general, this isn't true. But we can use the Takens theorem that can allow us to connect the real state with a surrogate state defined by a series of measurements. So suppose we have a time series defined with f is a operator measurement of our state that we can and we have a time series every time step n dt. We can map our dynamics in a space defined in a bending space of dimension d defined by our vector, and we can measure our distance now not in the real space but in this bending space. And we can optimize our parameter, define a technical inspired by the genetic algorithm defined by pruning and enriching approach. In this sense, given a master time series, we can generate a set of H replica with random parameter and state value, evolve evolve the replica, and every time that a measurement are available, we evaluate the distance between the master and the replicas in the embedding space. The half of them with the larger value are replaced with copy with small that are modified in parameter or in the state space with amplitude delta, like this came in this situation. We repeat the loop for m repetition, and after that we can see that the distance in the parameter space drop to 0 when the amplitude delta, the amount of variation that we do every measurement step, is sufficient. Is not too much small, essentially. But we can in this plot we can see the distance in case with parameter are random initialized. So if we start with delta sufficient big, we can move. We can explore all the state space, the parameter space, and we can find the right minimum. But in the opposite, if we use a delta too much small, we can explore the entire space, but with small delta we can obtain a better result when we are in a fine-tuning regime. In this case, we show the optimization problem when the parameter is like near the true value. So as if you are near the minimum, essentially, we can small move can allow us to reach better performance. So we define a parameter delta that change with the distance. In particular, we start with simply putting the change parameter as the distance that we measure between the master and the replica, and we can find that essentially the replica, starting with random position, move explore the entire parameter space, and then can when the distance drop to 0, we can obtain the true parameter. And that's all. Essentially, we in this case we ended the original Pecoral-Callo synchronization, starting with the Pecoral-Callo. We have two partial and intermittent coupling. So when we have only a partial information, or when we don't coupling every time step, but every time that we have a measurement that accessible. So, and we see that in this scheme, we can use this scheme to synchronize a master and a slave to obtain, using a simulated annealing or a pruning enriching approach, we can obtain the optimization of the parameter value. That's all. Essentially.
Any question? No small question? Okay, thank you again. Thank you. Allora, 25 minuti. Vabbè, comunque diciamo che in totale avete 25 minuti e 5 minuti prima Okay, third talk which is shared by Alberto Ortolani and Michele Baia, and the title is Neural Network Downscaling of Atmospheric Projection for Supporting Climate Resilience Initiatives.
Oh, no. Okay. Okay. Good morning to everybody. Yes, I mean, this is a shared presentation because, I mean, thanks for the opportunity. We are in some way new to this community. And so, I mean, this work we are going to present, it's a work in progress, and it was born by a cooperation between essentially Consorzio Lamma and the University of Florence. I belong to CNR, but also, I mean, I spend most of my working time at Lamma Consortium, which is a consortium made by CNR, so Italian National Research Council, and the Regional Administration of Tuscany. And Lamma is also the operational meteorological service of Tuscany. So maybe, I mean, for civil protection, but maybe you know the application for the meteorological forecast. If you don't know it, you can download and have a look, but this is another story. Here, let's say the need of this work on downscaling arise from a specific project, and I'm going to introduce some information about this project. So I will, let's say, speak about the project and the overall architecture of downscaling that we have thought with Michele, and then Michele will give you details on the specific approach, achieved with the neural network algorithm. The project is core, is an H2020 project, as you can see, the keywords are climate resilience and coastal cities. So essentially, the project is a big one. 20 partners with 12 countries. The duration is 4 years, and next June, we are reaching the half of the project, so the first 2 years. And the basic thing is to, in a sort of way, understand and targeting 4 major hazards in 10 coastal cities. One is Massa in Tuscany, then the other, some others. I just want to stress that one is Gdańsk in Poland, because some of you arise from that town. And we speak about coastal city living labs because one of the key aspects of the project is setting up these laboratories in order to involve local administration and citizens, voluntaries organization, and generally speaking, stakeholders, to increase literacy, awareness about the problem coastal, especially that they can have now, but especially thinking about the future, and the solution that could be implemented in order to facilitate the introduction of this solution in these cities. The hazards, as I was saying, are 4. So 3 are related to flooding. One is coastal flooding, so flooding essentially related to the tidal effect. Fluvial flooding, so classical flooding from rivers coming from inland, and then storm surge, so something related to the effect connected to waves and extreme waves. And then there is a long-term effect, which is coastal erosion. Not all cities are affected by all these hazards. Massa, for example, is affected by some of them, and foresee to be interested in targeting all. But just to talk about Gdańsk, for example, is interested in addressing the first 2, so the flooding, coastal and fluvial flooding. If you look, the website of the project, the very final objectives are related to this setting up this coastal city living lab for the reason I was telling you before, and especially to introduce the possibility to integrate ecosystem-based approach for addressing these problems. So something which is related to, using not engineering, pure engineering solution, but something use, natural opportunities, for example, sand dunes, or seagrass, or whatever you can think that are, identified in the project, listed and proposed to stakeholders. Then, if we think about, And another keyword is, in addition to ecosystem-based approach, is digital twin, a very fashionable word, in the sense that this is something which is built in the project in order to evaluate the impact of these solutions to, let's say, try to solve the existing and future problems. And then there is another number of things related also to increase the financial resilience for these cities, thinking about what is going to happen in the future with respect to what is, let's say, happening now. Anyway, the basic thing is to know what is happening in the future. So one of the key aspects is related to projection. So this is the structure of the project, and let's say what we are speaking about is the work related to this work package. So the regional and local projections, and essentially the objective of this work package is the downscaling of climate projections that are available on the global scale and are also on, let's say, more resolved scales. And then, of course, developing a number of tools to analyze this kind of data and verify what is going to happen at the local scale, which is something not directly inferable by, let's say, global projections, or even not so resolved projections. The point is that we were speaking about flooding. So the idea is that we need, and what we are doing is to, let's say, build a number of models in order to use this forcing data given by, let's say, global projections, and let's say, predicting what's going to happen on, let's say, on the hydrological side, so for what concern, of course, fluvial floods, on the wave side, for what concerns some surge, and also on the, let's say, oceanic side, thinking about, I mean, the coastal flooding. And then, of course, all these aspects are related also to the long-term erosion. So, I mean, we have a number of models, including, let's say, the last mile model, which is the hydraulic model, in order to understand which area will be eventually flooded with a given frequency in the future. So this is related again with financial resilience and also, I mean, a solution that could be implemented. But all these things are driven by the atmospheric forcing. And so, let's say, what you can imagine is that which can be, I mean, one of the questions is which can be a resolution, spatial resolution, suitable to, let's say, make reliable prediction. If you consider a watershed, it depends on the scale. This is, let's say, just a scheme of how an hydrological model can work. And of course, if you have basing like the one we have in Turkey, which is 10 of thousands of kilometers, square kilometers, let's say, no problem is the available resolution of the models, which at the moment arrive for what concern projections up to, let's say, 11 kilometers resolution. If you think about the city of Massa, we are dealing with a basin which is about 80 square kilometers. So let's say a grid point in this model, essentially. And so, I mean, from this point of view, knowing, for example, once precipitation is happening as an effect on runoff, and so consequently on the prediction of the events. So the idea is that, I mean, there are a number of global circulation models for, let's say, used for projections, but which are run with some tens of kilometers of resolution. But there are a number of projects that have already developed regional downscaling. So the one this here are the Eurocordex data, for example, that provide, as I was saying before, resolution data at a resolution of about 11 kilometers. And what we would like to do is to develop a strategy to downscale statistically this data to obtain gridded data to feed the other models that I was just mentioning before, and also to make a local downscaling, if you want, in a certain way to reproduce what a meteorological station could measure in the future. Here we are just concentrating this presentation on this aspect, and the strategy that we have, let's say, the method that we have thought to address is this one. I mean, assume that you have some, let's say, meteorological data set for a past period at the, let's say, resolution you would like to have also in the projection. You can, let's say, train a neural network in order to use this data and compare with other data that are the projection one, and use it in the projection mode. I explain a little bit better. I mean, here we have a reference data set. So consider something that is already developed for other reasons that we have it, and maybe Michele will give you some details. Then we have the projection that, of course, are data for the future, but a part of them is also run in the past. So in a certain way, we have an overlapping period. I don't want to mean that exactly overlap at the same time. I want to mean that they, let's say, overlap for a period where you can assume that you have the same statistics. So they are comparable. The problem is that these two, let's say, data sets are of course not synchronized, because I mean, at least this one is run freely, so not forced by the same, let's say, meteorological observation as normally this one that could be what we call the sort of reanalysis, so a model run but forced periodically with the observation. So the idea was let upscale this reference data set up to a resolution analogous of this historical data set. And in this case, of course, you have two data sets exactly synchronized, and train, let's say, a neural network to reproduce this finer scale resolution data from this coarser resolution one. When you have trained this, let's say, neural network, you should be able to use it in the projection mode, provided that, I mean, the two data sets, this one upscaled, so that we call the surrogate, and the other one, the historical data set, have more or less the same statistics. So let's say, eventually you need an additional step, which is to connect these two statistics, and this could be achieved by, let's say, an approach of probability matching, so essentially integrate the cumulative distribution functions. Anyway, the things we are going to speak, oops, sorry. Okay, now is this one. So is the neural network developed to, let's say, make this downscaling. And now I give the floor to Michele, because Michele developed this specific algorithm, so it's much better than me to explain this one.
Okay, so the idea is, given this model, we want to try to find a way to obtain a better resolution. We can do in two ways, dynamical or statistical. In the dynamical sense, we essentially reinitialize the model and integrate with the physics, the whole physics at the scale that we want to obtain. And or we can use a statistical method, so statistical mapping between the two different scale, spatial or temporal. In this case, we consider only spatial scale, and that can be done with a different approach in a method of analogy or statistical regression on weather generation. The last of those, last two can be done with the neural network approach. In our work, we consider essentially a statistical regression, based essentially to define a neural network to mapping a low resolution or surrogate model to a high resolution or reference model. The data set are obtained from a dynamical downscaling of the ERA5 data set from other work done at the Lama Meteo. We use 12 years for the training and the testing, the device in 50C50. The frequency of the data set are every 3 hours. So we have offset to a measurement of every 3 hours. To obtain the cross grain, the input of our neural network, we do a whole grain of cross grain of the reference model as as average of the first neighbor, obtain at the resolution to obtain the resolution of the projection model, the Met Cortex, that can be used to to do the rest of the project. We use essentially this predictor to predict our model. We use pressure at the level C, humidity, temperature at 2 meters, precipitation, and the component UV of wind at 10 meters. And also we use spatial information at the 2 resolution, in particular latitude, longitude, orography, so and land use, how the land are used in this model, in this place. And to do the scaling, we divide the scaling in 2 different steps, essentially, train it one after the other. Local downscaling based and I don't know what's up, a field reconstruction of the local downscaling using the spatial weight layer defined like a dense layer. In the local downscaling, essentially what we will do is consider a neighbor of a pixel in the surrogate model, the low resolution, and its neighbor, and we consider all the variable that we use, so the variable and the spatial information. We feed together in a convolution 2D to obtain a vector that represent some feature of that extract. We use a convolution 2D that extract the feature in a given time step to take in account eventually the dynamics of the local dynamics of the model. We consider a time window of period W, and so we feed in the network all this time to obtain all this feature for a single time, and that those one are used to input in a recurrent neural network, and the output are projected in essentially with this vector S that represent all the spatial information of the high resolution model. So given a point, a pixel in the surrogate model, in the low resolution model, we can obtain a feature map of dimension n that are the dimension of the spatial neighbor pixel in the high resolution model. So in this sense, we map a single point in a feature of n spatial neighbor that represent the pixel in the high resolution model. Then we can, given this feature for every input, we do this one for every pixel in the low resolution model. We can reconstruct the whole field using this spatial weight diagram. Essentially, for every pixel, we obtain a region that can be that represents the local predictor. This predictor can have an overlap, and for that we define a weight. Essentially, is a fully connected with some modification, but is essentially a fully connected layer that reconstruct the whole field. In the case of the precipitation downscaling, we define not one but 2 different spatial weights that during the training, to take into account that the difference influence that the low resolution pixel can have to its neighbor, because we can have that given our pixel in the low resolution that is wet defined as a precipitation upper to a threshold shows for physical by physical assumption. We can have that a pixel in a low resolution can be wet, and its neighbor in the low resolution model dry. but for the high resolution model, we can have that a bigger area are wetted. So to take in account the fact that taking account essentially that the preservation field it isn't spatial continuous, it isn't smooth, spatial smooth, but can have some peak of fractal. There we show some result, in particular for the precipitation and the relativity immunity obtained for on a test set, obviously. We can see that starting with this field, and we want to reconstruct this situation, we obtain a situation like that. So essentially, the net can reconstruct the spatial information, obviously losing some local information, and the matching between the predicted and the true value are for smooth field like relativity humidity, temperature is almost good, but for precipitation we need to do better improvement. But sometimes it do a good result. It depends on the intensity, obviously, and the type of pattern that before, because this pattern these patterns are typically because are essentially a holographic precipitation, so occur in your model occur more times, so the network can be learn this feature, but in general, this is not obvious. Almost. So essentially, with this architecture we can this architecture can be used to downscale in a statistical sense this atmospheric variable, but we need to do a deep study in the quality of the training, in a sense that we need to check if the overfitting or if we can improve or training by hyper optimization without the optimization of the parameter, and also we need to do a statistical analysis of the probability matching to be sure that we can use this neural network trained on data set based essentially on that data in the past can be used to downscale data projection data, so data in the future that we don't have. So thank you.
Yeah, sure. Questions to one of the two speakers? Yeah.
So wind speeds, have you also compared it, like how your neural network compares to just simpler forms such as interpolation or things like that? Like, yes, a simpler approach, or are you planning to do that?
Yeah, we have done some, or I don't have any. Yeah, we are trying. We have obtained some result, but we are not to obtain a good reconstruction. Statistical, we have in a statistical approach, in a sense, the 1 year or more than 1 year, we can obtain good result in a statistical sense, but we cannot reconstruct really well the field that as we can be obtained with the neural network approach. So we are preferred to use this one too, also because neural network is you can use as name.
Maybe I can just integrate this answer. In the sense that, of course, we have several objectives for this work. So first of all, we have to understand if this kind of downscaling really gives some added value with respect to the forcing terms that we have to use for the other models. I mean, I didn't specify, but the other models are run in the physical way. So I mean, they are nested because they have to interact with structures that are topography, orography, and also, I mean, coastal areas, and you cannot do it statistically. So from this point of view, we need to run waves in physical model from this. For atmosphere, of course, could be better, but it could be a project in the project. So from this point of view, we try to use a simplified approach, which is this one. Anyway, I mean, so we have to verify, first of all, if there is an added value. And then, I mean, your point is good. I mean, is this added value, let's say, even independently on the application, really comparable or not for what you obtain with simpler approaches? Well, I mean, we have to do it, of course. I mean, I guess that for considering rainfall, which is, as you can imagine, the most interesting parameters, this is not the case, because generally speaking, I mean, let's say precipitation is an intermittent phenomena with, I mean, specific features that, of course, are not so smooth. And then simplified approaches normally do not give, let's say, reliable results. And even this one, I mean, precipitation is the most tricky parameter, because, I mean, if you look at, I mean, this is a relative humidity. If you look also to temperature or pressure, of course, they are much more simple. Okay, so maybe if you go even some, okay, but anyway, so from this point of view, could be the case that even simplified, let's say, methods could work at the same time. But probably this is not so relevant for, I mean, what is easy probably is not going to give us a real added value with respect to the application we have to do with this data. So, but it's something that we have to do.
Yeah.
Very interesting. Have you tried to use some kind of already trained super resolution model to upscale the resolution there instead of training your own one, or is it something that you have avoided due to
Fine-tuning approach?
Yeah, more or less, yeah.
Honestly, no. Honestly, I don't know. Maybe it's a good idea to try if it can be a good result. I don't know, because checking this in this study, I understood that the important things are these vector S that represent essentially all the spatial information in the resolution model. In this sense, the network can map the pattern in the variable to the specific to the specific latitude or longitude.
So yeah, if I'm getting it right, your approach is more on the side of extracting relevant features and then learning the dynamical system for the upscaled model. Am I getting this right? More or less?
Yeah, more or less, maybe yes. It is
okay, instead of just pure super resolution thing. So, okay.
Yeah, it could be. I'll try. Maybe I need to try to.
Yeah, maybe just the first part and will be faster. Just,
yeah.
Okay, thank you.
Oh, thank you.
Other questions? Yes, one.
You use a number of predictors, right? It was on the slide.
Yeah, I use all the predictor to predict one single variable. I've tried also for different variable, for this predicted variable, to check essentially a correlation and maybe try to eliminate one of them.
So in this list, these are parameters that you are predicting, or these are parameters that are used as input? I'm a little bit confused.
Okay, I'll say this is a simple scheme. As predicting as input, I feed all the as you can see, is essentially a stack of the. So in this case, I want to obtain temperature. I put as input all the predictor. So this six variable and spatial information.
Yeah.
At the low resolution, there spatial information at the high resolution.
Okay.
Compare.
Then in that case, do you know which predictors are most important?
Yeah, I do a statistical. I try a statistical correlation first to show is which is important, which not. Honestly, I try also to using all the most relevant and all, and doesn't see really difference. So I need to check better if is for the network is better to have all the variable to, or if are too much and maybe like the net, if I put all the prediction, maybe the network learn things that aren't true. But for now I don't have really the idea of what is the best way.
Okay. I was also going to comment on what was said earlier, that there is a lot of commercially available tools that are used for resolution, for increasing the resolution. Now, the difference here, of course, is that you're also involving a time series.
Exactly. Yeah.
But and I'm definitely not specialized in this, but I would also suggest that you look into sort of resolution increasing algorithms for videos.
Okay.
Yeah.
Okay. Yeah, okay. I need to check that.
Because there's a lot available. Huh.
Okay.
Okay, thank you.
Thank
Really
you.
interesting.
Thank you.
Okay, I think that we can stop. Thank again all the organizers. Now is a coffee break, and we are back at 11:30.